Hello there, and welcome. Tonight, we're embarking on a journey unlike any other. A journey not through space, but through time itself, back to the very beginning, to a moment so profound, so impossible to truly comprehend, that it remains one of the greatest mysteries ever contemplated by human minds. Tonight, we're traveling to the birth of the universe itself. From nothing to everything, from silence to stars, from emptiness to all that is. Before we begin this cosmic voyage, let yourself settle into comfort. Find a position where your body can rest completely. Feel the surface beneath you supporting your weight. Let your shoulders drop. Allow your breathing to find its own gentle rhythm. There's nowhere you need to be, nothing you need to do. Just listen and let your mind drift through the story of creation itself. If you enjoy these quiet journeys through the cosmos, I invite you to like, subscribe, or share your thoughts below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe, close your eyes if you wish, and let's travel back to the very beginning of everything. We live in a universe that is almost incomprehensibly vast, hundreds of billions of galaxies, each containing hundreds of billions of stars, planets beyond counting, space stretching so far in every direction that light itself, traveling at 186,000 miles per second, would need billions of years to cross it. Everything you see around you, every atom in your body, every particle of light from every distant star, all of it came from somewhere. All of it has an origin story, and that story begins approximately 13.8 billion years ago, in a moment we have come to call the Big Bang. But the Big Bang is not really a bang at all. It wasn't an explosion in space, it was an explosion of space itself. And when we ask what came before it, we're asking a question that may not even have an answer, because before might not exist in any way we can understand. Time itself began with the universe. Space itself was born in that instant. Cause and effect, the very logic we use to make sense of our world, breaks down when we approach the beginning of everything. Tonight, we'll trace the story of our universe from its first incomprehensible instant through the emergence of matter, energy, light, and structure. We'll encounter moments measured in fractions of seconds, temperatures so extreme that atoms couldn't exist, densities so intense that our mathematics struggle to describe them. We'll meet the quantum fluctuations that became galaxies, the cosmic background radiation that still whispers of that ancient beginning, and the mysterious dark matter and dark energy that shape the universe we observe today. This is a story told in the language of physics and cosmology, but it's also a meditation on existence itself, on how something can emerge from what appears to be nothing, on how the universe not only came to be, but how it came to be in exactly the way that allows you and me to be here, contemplating its origins. So settle deeper now, let your breathing slow, and let's begin at the beginning, or as close to it as human understanding can reach. Imagine, if you can, a point, not a small point, but a mathematical point with no size at all. 0 dimensions, no width, no height, no depth, and yet within this point, compressed beyond any possible imagining, was all the mass and energy that would one day become our entire observable universe. Every galaxy, every star, every planet, every atom that would ever exist, all contained in something smaller than the smallest thing you can imagine. This is what physicists call the singularity, a place where the normal rules of physics cease to function, where our equations fill with infinities and our understanding reaches its limit. At the singularity, density becomes infinite, temperature becomes infinite. Space-time itself, the very fabric of reality, curves into shapes our minds cannot picture. The singularity is not a place in space, because space itself doesn't exist yet. It's not a moment in time, because time hasn't begun. It simply is or was a condition so extreme that our most sophisticated theories can only gesture toward it from a distance. Scientists describe this initial state using numbers that seem more like science fiction than science fact. We're talking about an instant so brief it defies comprehension, the Planck epoch, lasting from time 0 to approximately 10 to the negative 43 seconds after the beginning. That's a decimal point followed by 42 zeros and then a 1. Try to picture a trillionth of a trillionth of a trillionth of a trillionth of a second. You're still not even close. This is the frontier where quantum mechanics and gravity meet, where our two most successful theories of physics both claim jurisdiction but cannot yet speak the same language. The Planck time is not arbitrary. It emerges naturally from the fundamental constants of nature, the speed of light, the gravitational constant, and Planck's constant from quantum mechanics. When you combine these three numbers in just the right way, you get a time scale of about 10 to the negative 43 seconds and a length scale of about 10 to the negative 35 meters. These are the Planck scales, the smallest meaningful measurements of time and space. Below these scales, our current understanding of physics simply breaks down. Space and time become quantum objects themselves, fluctuating and uncertain. At the Planck scale, the energy density was so extreme that every cubic centimeter of space contained more energy than all the visible matter in the observable universe today. The temperature was around 10 to the 32nd power degrees Kelvin, a number so vast it loses all meaning. At such temperatures, there's no distinction between particles and forces, no separation between matter and energy. Everything is unified in a way that we can barely conceive, let alone calculate. During the Planck epoch, based on our best theoretical models, the universe may have existed in a state physicists sometimes call quantum foam. According to these theories, space and time themselves were not smooth and continuous as we experience them, but potentially granular and chaotic, seething with possibility. You might imagine space-time not as a calm fabric, but as a roiling ocean at the quantum scale, with tiny black holes spontaneously forming and evaporating, with wormholes appearing and disappearing, with the very geometry of reality fluctuating wildly from moment to moment. Though we cannot yet test these ideas directly, they emerge naturally from attempts to combine quantum mechanics with gravity. At this point, all the fundamental forces of nature, the forces that govern how matter and energy interact, were unified into a single force. Gravity, electromagnetism, the strong nuclear force that binds atomic nuclei together, and the weak nuclear force that governs radioactive decay. All of these were one. The universe was in a state of perfect symmetry, a condition of such extreme energy and temperature that the distinctions we see today simply didn't exist. String theory, one of the leading attempts to describe this era, proposes that the universe during the Planck epoch may have had 10 dimensions, not the 4 dimensions of space-time we experience today. According to this theoretical framework, 6 of these dimensions would have been compactified, curled up into shapes so small they hide between the particles we can measure, while 4 dimensions, 3 of space and 1 of time, expanded to become the universe we inhabit. While string theory remains unproven, it represents one of our most sophisticated attempts to understand this earliest epoch. But here's where the mystery deepens. What triggered the universe to emerge from this quantum foam? What caused the singularity to give way to expansion? Scientists honestly do not know. Some theories propose that the universe emerged from quantum fluctuations in a pre-existing quantum vacuum, a state that's not truly nothing, but a seething sea of virtual particles and potential energy. Others suggest that our universe might be one bubble in an infinite multiverse, constantly spawning new universes from quantum events. Still others propose that time is cyclical, that our universe is one iteration in an endless series of expansions and contractions. The deepest truth is that we're asking questions at the very edge of what physics can address. We're trying to understand a condition where our concept of causation may not apply. We're asking what came before. Might be like asking what's north of the North Pole. The question itself may be based on assumptions that don't hold at the boundary of existence. Yet from this unfathomable beginning, somehow the universe emerged. And what happened next, in the first tiny fractions of the first second, set the stage for everything that would follow. The singularity gave way to expansion. The quantum foam settled into something more stable, and a process began that would ultimately lead to stars, planets, and the remarkable fact of your existence, lying here listening to this story about where it all began. Take a deep breath now. Let the weight of this beginning sink in. Everything you are, everything you know, everything that exists traces back to that impossible starting point, and from that point, the universe began to unfold. Inflation, the universe's first growth spurt. After the Planck epoch, something extraordinary happened, something so rapid, so dramatic, that it reshaped our entire understanding of cosmic origins. The universe didn't just expand, it inflated. It underwent a period of exponential growth so intense that it makes everything that came after seem slow by comparison. This is the theory of cosmic inflation, first proposed by physicist Alan Guth in 1980, and it remains one of the most elegant solutions to some of cosmology's deepest puzzles. Picture Guth, a young researcher at Cornell University, sitting in a lecture hall in 1978, listening to astronomer Robert Dicke discuss something called the flatness problem. The universe, as far as we can measure, appears to be geometrically flat. Its density is almost exactly at what's called the critical density, the point between eternal expansion and eventual collapse. But this flatness is incredibly unstable. Any tiny deviation from perfect flatness in the early universe would have been magnified over billions of years. The universe should have either collapsed back on itself long ago or expanded so rapidly that no structures could form. Yet here we are, in a universe that's remarkably, improbably flat. Guth kept returning to this problem, turning it over in his mind. And then, in December of 1979, he had an insight that would change cosmology. What if, in its earliest moments, the universe underwent a brief but incredibly intense period of exponential expansion? Not just growing, but doubling in size again and again in impossibly short intervals, driven by a quantum field called the inflaton field. Guth's eureka moment came while he was working on a completely different problem, the magnetic monopole problem. Grand unified theories of particle physics predicted that the early universe should have produced massive numbers of magnetic monopoles, particles with only one magnetic pole. These monopoles should be everywhere, outnumbering ordinary particles, but we've never detected a single one. Where did they all go? Guth realized that if the universe underwent a period of exponential expansion after the monopoles formed, they would be diluted to such a degree that finding one would be nearly impossible. The expansion would spread them so thin across the cosmos that our entire observable universe might contain none at all. But as Guth worked through the mathematics, he realized that this inflationary expansion solved far more than just the monopole problem. It solved the flatness problem. It solved the horizon problem. It even provided a mechanism for generating the density fluctuations that would become galaxies. In his notebook that night, he drew a double box around his conclusion and wrote, "Spectacular realization." It was one of those rare moments in science when a single idea suddenly makes sense of multiple puzzles simultaneously. The numbers are staggering. During cosmic inflation, which theoretical models suggest lasted from approximately 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang, the universe expanded by a factor of at least 10 to the 26th power. That's 10 million billion times larger. In a span of time so brief it would take more words than exist in all human languages to describe, the universe went from smaller than a proton to larger than a galaxy. Imagine a bacterium suddenly inflating to the size of the Milky Way. That barely captures the scale of this expansion, and it happened faster than the speed of light. Not because anything was moving faster than light through space, but because space itself was expanding at this mind-bending rate. The fabric of reality itself was stretching, carrying everything along with it. But inflation wasn't just about speed. It solved multiple problems that had puzzled cosmologists. There was the flatness problem Guth had been pondering. Inflation explains it beautifully. Just as blowing up a balloon makes its surface appear flatter and flatter locally, inflation stretched the universe so enormously that even if it started with significant curvature, it would appear flat to us now. The observable universe we can see is just a tiny patch of a much larger whole, and that tiny patch appears flat because it's been stretched smooth. Then there's the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang that fills all of space, we see that it has almost exactly the same temperature in every direction we look. The difference is only about 1 part in 100,000. This suggests that the entire observable universe was once in thermal equilibrium, that all parts of it were in contact long enough to reach the same temperature. But without inflation, there wasn't enough time for this to happen. Different regions of the early universe would never have been able to exchange energy with each other. They couldn't have coordinated to reach the same temperature. Inflation solves this elegantly. Before inflation, the entire region that would become our observable universe was indeed small enough for all its parts to be in causal contact, to communicate and reach equilibrium. Then inflation stretched it out tremendously so that regions that were once close neighbors are now separated by distances so vast that light hasn't had time to travel between them even after nearly 14 billion years of cosmic history. The universe appears uniform because it was uniform before it was inflated. There's also the magnetic monopole problem. According to theories of particle physics called grand unified theories, the early universe should have produced vast numbers of magnetic monopoles, hypothetical particles that have only one magnetic pole, north or south, rather than both. These monopoles should be everywhere, as common as protons and neutrons. But we've never found one. Inflation explains this too. If monopoles formed before inflation, they would have been diluted so tremendously by the expansion that we'd be extraordinarily unlikely to ever encounter one. The mechanism behind inflation is a quantum field called the inflaton field, which filled all of space in the earliest universe. This field was in what's called a false vacuum state, a condition that looks like emptiness but actually contains enormous energy. Think of it like a ball balanced on a hill. It's in equilibrium, but it's not the lowest energy state it could be in. Eventually, it will roll down. When the inflaton field was in this false vacuum state, it created a repulsive gravitational effect, a kind of anti-gravity that drove the exponential expansion. The energy density of this field remained nearly constant even as space expanded, which is a bizarre property that's hard to wrap your mind around. Normally, if you expand something, its density goes down, but the inflaton field didn't work that way. It kept pumping energy into the expansion, driving it faster and faster. Then suddenly, inflation ended. The inflaton field transitioned to its true vacuum state, like the ball finally rolling down the hill. This transition was called reheating because all that energy locked up in the inflaton field was released as a flood of matter and radiation. The universe, which had become cold and empty during inflation due to the rapid expansion, was suddenly filled with particles and energy. This is what we typically think of as the Big Bang, the hot, dense beginning. But it wasn't really the beginning. The beginning was earlier, in the quantum foam and the singularity. The Big Bang was more like a consequence, the aftermath of inflation. And here's something profound. Inflation left its fingerprints. During the inflationary period, tiny quantum fluctuations in the inflaton field were stretched to cosmic scales. These microscopic variations in the density of the field became variations in the density of matter and energy after inflation ended. And those variations, those slight irregularities, became the seeds of all cosmic structure. Every galaxy, every star, every planet traces its existence back to quantum fluctuations during the inflationary epoch. The randomness of quantum mechanics, amplified to astronomical scales by inflation, determined where matter would clump and where it would thin out. The structure of the universe, the distribution of galaxies across billions of light years, began as quantum noise. Scientists are still testing inflation theory, looking for evidence in the patterns of the cosmic microwave background and in the large-scale structure of the universe. So far, the observations match the predictions remarkably well. The slight variations in the temperature of the cosmic microwave background, the way galaxies are distributed, the flatness of space, all of these align with what inflation predicts. But questions remain. What exactly was the inflaton field? Was it a single field or multiple fields? What ended inflation, and did it end everywhere at the same time? Or are there regions of the larger universe where inflation is still happening, spawning new pocket universes eternally? These questions push against the boundaries of what we can know, but they're being actively pursued by physicists and cosmologists around the world. For now, breathe deeply and picture it. In less than a trillionth of a trillionth of a trillionth of a second, the universe exploded from quantum scale to vast, beyond comprehension. Space itself stretched, carrying the seeds of everything that would come. And when inflation ended, the universe was primed for the next chapters of its story, ready to begin the slower but still extraordinary process of becoming the cosmos we inhabit today. The first second, a symphony of particles. After inflation ended, the universe found itself in a new state. It was still incredibly hot, incredibly dense, but it was no longer expanding at that frenzied, exponential rate. The expansion continued, but more sedately, governed now by the ordinary laws of gravity and thermodynamics. And in this hot, dense cauldron, the fundamental building blocks of matter began to take shape. The temperature at this point defies imagination. We're talking about energies of around 10 to the 15th power degrees Kelvin, or 1,000 trillion degrees. At these temperatures, the very idea of atoms is meaningless. Matter, as we know it, cannot exist. Instead, the universe was filled with a soup of fundamental particles and radiation, all interacting intensely, transforming back and forth between different forms. The first major transition came as the universe continued to cool. At around 10 to the negative 36 seconds after the beginning, as inflation ended, the unified force that had governed the Planck epoch broke apart. Gravity separated first, becoming its own distinct force, governed by the warping of space-time. The universe now had gravity pulling things together and the inflaton field's leftover energy spreading things apart, though the latter was fading rapidly. Then came another separation. The strong nuclear force, which would eventually bind quarks together to form protons and neutrons, split off from what remained of the unified force, which now became the electroweak force, a combination of electromagnetism and the weak nuclear force. This happened at around 10 to the negative 12 seconds, when the universe was about 1 trillionth of a second old. The temperature had dropped to a mere 1,000 trillion degrees. At this point, the universe was dominated by quarks, electrons, neutrinos, and their corresponding antiparticles, all bathed in intense radiation. Quarks are the fundamental particles that make up protons and neutrons. They come in 6 types, or flavors, with whimsical names like up, down, strange, charm, top and bottom. But at these extreme energies, quarks couldn't bind together yet. They existed in what's called a quark-gluon plasma, a state of matter so hot and dense that quarks and the particles that carry the strong force called gluons moved freely rather than being confined inside protons and neutrons. Here's something profound that happened during these early moments. The universe was filled with both matter and antimatter in almost equal amounts. For every quark, there was an antiquark. For every electron, a positron. And when matter and antimatter meet, they annihilate each other in a flash of pure energy. This should have been catastrophic. All the matter and antimatter should have destroyed each other, leaving only radiation. But there was a slight imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. This tiny asymmetry, just one part in a billion, made all the difference. The matter and antimatter annihilated each other, releasing vast amounts of energy, but when the process was done, there was still matter left over. That leftover matter, that one part in a billion, is everything we see today. Every star, every planet, every atom in your body exists because of this minuscule asymmetry between matter and antimatter in the first second of cosmic history. This matter-antimatter asymmetry is called baryogenesis, the creation of an excess of baryons, particles made of three quarks like protons and neutrons over antibaryons. The exact mechanism that created this asymmetry is still being researched, but it must have involved processes that violated certain symmetries in physics. One possibility involves the weak nuclear force, which treats matter and antimatter slightly differently. Another involves exotic particles that existed only in the extreme conditions of the very early universe and decayed in ways that favored matter over antimatter. Without this asymmetry, the universe would be filled with nothing but photons, light without substance, and we would not exist to contemplate our origins. Why this asymmetry existed remains one of the great mysteries of physics. Current theories suggest it may have arisen from subtle differences in how matter and antimatter interact with the weak nuclear force, a phenomenon observed in particle physics experiments. Other proposals involve more exotic explanations with particles and interactions we haven't discovered yet, but the complete mechanism remains under investigation. What we know with certainty is that this imbalance existed because we're here to observe its consequences. Without it, the universe would be filled with nothing but light, and we wouldn't exist to wonder about our origins. As the universe continued to expand and cool, more changes came quickly. At about 10 to the negative 12 seconds, the electroweak force split into electromagnetism and the weak nuclear force. Now all four fundamental forces, gravity, electromagnetism, the strong force, and the weak force, were distinct. The universe had settled into the physical laws we recognize today, though the conditions were still far more extreme than anything we experience in our ordinary lives or can recreate in our most powerful particle accelerators. Then came a crucial transition. At around 1 microsecond after the beginning, when the universe was about 1/1,000,000th of a second old, the temperature had dropped enough that quarks could finally bind together. The quark-gluon plasma condensed into protons and neutrons, the building blocks of atomic nuclei. This is called the quark epoch, and it marks the moment when the fundamental constituents of ordinary matter came into being. The protons and neutrons that make up every atom in your body, in the earth, in the sun, and stars, all came into existence during this brief period, but they were not yet bound into atomic nuclei. The temperature was still too high. Free neutrons bounced around, colliding with protons and electrons. Protons captured electrons briefly, then released them again. The universe was still too violent for anything more complex than individual particles to survive. As we approached the 1-second mark, the conditions began to moderate slightly. The temperature had dropped to about 10 billion degrees, which sounds extreme but is actually cooler than the core of the most massive stars. Neutrinos, ghostly particles that barely interact with anything, decoupled from the rest of the matter and radiation. They stopped colliding with other particles and began to stream freely through space. Those neutrinos are still out there, filling the universe, though they're almost impossible to detect. They form a cosmic neutrino background, similar to the cosmic microwave background, but even more elusive. By the time the universe was 1 second old, the temperature had fallen to about 1 billion degrees. The era of particle creation was over. The fundamental building blocks were in place. Now the universe could begin the next phase of its evolution, building those blocks into more complex structures. But before that could happen, there would be a brief but critical period where the first atomic nuclei would form, setting the stage for everything that would come after. Feel the pace of this first second. In less time than it takes you to draw a single breath, the universe went from a state of unified forces and exotic particles to a cosmos filled with the familiar ingredients of matter, ready to begin assembling themselves into atoms, molecules, stars, and eventually life itself. The first second set the rules, created the pieces, and prepared the stage for the magnificent unfolding that would follow. Nucleosynthesis, the forging of elements, 3 minutes. That's how long it took for the universe to create the raw materials for all future chemistry. 3 minutes after the beginning, when the universe was still unimaginably hot and dense, but had cooled enough for a crucial process to begin. This is the epoch of Big Bang nucleosynthesis, and it's one of the most precisely understood chapters in cosmic history. Picture the universe at 1 second old. It's filled with protons, neutrons, electrons, and a sea of radiation. The temperature is about 1 billion degrees Kelvin. At this temperature, protons and neutrons are bouncing around freely, occasionally sticking together briefly but immediately being blown apart again by high-energy collisions. The universe is still too violent for stable atomic nuclei to form. But as the expansion continues, the temperature drops, and at around 1 minute after the beginning, something remarkable becomes possible. The temperature has fallen to about 100 million degrees, which is still far hotter than the core of the sun, but cool enough that protons and neutrons can begin to fuse together and stay fused. The first step is simple. A proton and a neutron combine to form deuterium, an isotope of hydrogen with 1 proton and 1 neutron in its nucleus. This process had been tried countless times in the first minute, but the energetic photons filling the universe kept blasting the deuterium nuclei apart in a process called photodisintegration. Now finally, the photons have cooled enough that deuterium can survive. Once deuterium forms, the rest follows quickly. 2 deuterium nuclei can fuse to form helium-3, which has 2 protons and 1 neutron. Deuterium and helium-3 can combine to form helium-4, the most common form of helium, with 2 protons and 2 neutrons. Some of these reactions produce tritium, another hydrogen isotope with 1 proton and 2 neutrons, which can also fuse with deuterium to make more helium-4. This flurry of nuclear fusion lasts only about 15 minutes. By the time the universe is 20 minutes old, it has cooled too much for these reactions to continue. The temperature has dropped below 10 million degrees, and that's not hot enough to overcome the electrical repulsion between positively charged atomic nuclei. The nucleosynthesis window closes. In those 15 minutes, about 25% of the universe's ordinary matter by mass was converted from hydrogen into helium-4. Tiny amounts of deuterium, helium-3, and lithium-7 were also created, but that was it. No heavier elements formed. The conditions weren't right for creating carbon, nitrogen, oxygen, or any of the other elements essential for life and planets. Those would have to wait for stars to form billions of years later. This prediction that the universe should be roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium, is one of the great triumphs of Big Bang theory. When astronomers look at the oldest stars and gas clouds, they find exactly this ratio. No matter where they look, the proportion of hydrogen to helium matches what the theory of Big Bang nucleosynthesis predicts. It's one of the most precise confirmations we have that this story of the universe's first minutes is fundamentally correct. The leftover deuterium is particularly important as a cosmological probe. Deuterium that forms in stars gets destroyed quickly by fusion reactions, so any deuterium we observe today must be primordial, left over from the Big Bang. By measuring how much deuterium exists in old metal-poor gas clouds, astronomers can work backward to figure out the density of ordinary matter in the early universe. These measurements have helped determine that ordinary matter, the stuff that makes up atoms and molecules, accounts for only about 5% of the total mass and energy of the universe. The rest is dark matter and dark energy, which we'll explore later in our journey. After nucleosynthesis ended, the universe entered what might seem like a period of calm, but it was really a time of waiting. The universe was now filled with atomic nuclei and free electrons, all bathed in intense radiation, but it was still too hot for atoms to form. If an electron tried to orbit a nucleus, it would immediately be knocked away by a high-energy photon. The universe was opaque, foggy with constantly interacting matter and light. Photons couldn't travel far before scattering off an electron. It was like trying to see through a dense cloud. This state would persist for hundreds of thousands of years. The universe continued to expand and cool, but slowly, methodically. The temperature dropped from millions of degrees to hundreds of thousands of degrees to tens of thousands of degrees. The density decreased as space itself grew larger, and all the while, the matter and radiation remained tightly coupled, unable to separate from each other. During this time, something else was happening in the shadows. Dark matter, which doesn't interact with light or ordinary matter except through gravity, was beginning to clump. Slightly denser regions of dark matter were pulling more dark matter toward them, creating the first structures in the universe. These dark matter clumps would eventually become the gravitational scaffolding for galaxies, but for now, they were invisible, influencing the universe through gravity alone, while ordinary matter remained trapped in its dance with radiation. The universe was pregnant with potential. The seeds of structure, planted as quantum fluctuations during inflation, were beginning to grow in the dark matter distribution. The atomic nuclei that would one day form the cores of atoms were in place. All that was needed was time for the universe to cool enough for the next great transition, when light would finally break free and atoms could form, ushering in a new era of cosmic evolution. Breathe in this moment of waiting. The universe at a few minutes old had already accomplished so much, had already set the fundamental composition of matter, but it was just beginning. The real magic, the formation of stars and galaxies and planets, was still to come, and it all depended on what would happen next. In the great decoupling of light and matter, the moment when the universe became transparent and left us an echo we can still detect today. The moment of last scattering, when light broke free. For nearly 380,000 years, the universe was opaque. Light and matter were locked in an intimate embrace, photons constantly colliding with free electrons, unable to travel more than a short distance before being scattered in a new direction. It was as if the entire universe were filled with a luminous fog, glowing intensely but impossible to see through. But then, gradually, inexorably, the universe cooled. And when the temperature dropped below a critical threshold, everything changed. This moment is called recombination, though that's a bit of a misnomer because the electrons and nuclei had never been combined before. A better name might be combination, but recombination is the term that stuck. What happened was this. The universe cooled to about 3,000 degrees Kelvin, roughly half the temperature of the sun's surface. At this temperature, electrons no longer had enough energy to escape when they encountered an atomic nucleus. They could finally settle into orbit around protons, forming stable hydrogen atoms. In regions where there were helium nuclei, electrons could attach to those as well, forming helium atoms. This process happened relatively quickly, cosmically speaking, over a span of about 100,000 years. But the effect was profound. Once the electrons were bound into atoms, photons no longer had free electrons to scatter off of. The photons that had been trapped, bouncing endlessly from electron to electron, were suddenly free to travel through space unimpeded. The universe became transparent. This is one of the most important moments in cosmic history because it left us something extraordinary, a snapshot of the universe at 380,000 years old. The photons that were released at the moment of recombination have been traveling through space ever since, and we can still detect them today. They form what's called the cosmic microwave background, or CMB, a faint glow of radiation that comes from every direction in the sky and carries information about the conditions in the very early universe. The discovery of the cosmic microwave background is itself a wonderful story. In 1948, physicists Ralph Alpher and Robert Herman, working with George Gamow on Big Bang nucleosynthesis, predicted that there should be leftover radiation from the Big Bang, cooled by the expansion of the universe to about 5 degrees above absolute zero. At the time, this prediction didn't get much attention. Then, in 1965, two radio astronomers at Bell Laboratories in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn antenna designed to detect radio signals from satellites, but they kept picking up a persistent noise, a hiss that came from all directions in the sky equally. At first, they thought it might be interference from New York City, or even from pigeons nesting in the antenna. They cleaned out the pigeon droppings, checked their equipment meticulously, and the noise remained. Meanwhile, just 60 kilometers away at Princeton University, physicist Robert Dicke and his team were preparing to build a telescope to search for the primordial radiation predicted by Big Bang theory. When Penzias heard about their work through a colleague, everything clicked into place. The noise they had been trying to eliminate wasn't noise at all. It was the cosmic microwave background, the afterglow of the Big Bang itself. Penzias and Wilson had accidentally made one of the most important discoveries in the history of cosmology. They shared the 1978 Nobel Prize in Physics for their work, and their discovery provided powerful evidence that the Big Bang theory was correct. Alternative theories, like the steady-state model that proposed the universe had always existed in roughly its current form, couldn't explain the cosmic microwave background, but Big Bang theory predicted it exactly. The CMB has a nearly perfect blackbody spectrum, which means it has the distribution of wavelengths you'd expect from a thermal object at a specific temperature. That temperature today is about 2.7 degrees Kelvin, or negative 270 degrees Celsius, just barely above absolute zero. The expansion of the universe has stretched the wavelengths of these photons enormously. What was once visible light, or even higher energy radiation, has been red-shifted down to microwave wavelengths. That's why we call it the cosmic microwave background. The precision of this blackbody spectrum is actually astonishing. Measurements from the COBE satellite in 1990 showed that the CMB's spectrum matches theoretical predictions to better than 1 part in 100,000. This is the most perfect blackbody spectrum ever measured in nature, more precise than anything we can create in a laboratory. It's a testament to how thoroughly mixed and thermalized the early universe was before recombination. But the CMB isn't perfectly uniform. There are tiny variations in temperature, about 1 part in 100,000. In some directions, the CMB is slightly warmer, about 2.725 Kelvin, and in others, slightly cooler, about 2.723 Kelvin. These variations, called anisotropies, are incredibly important because they map the density variations in the early universe. The slightly warmer spots correspond to regions that were slightly denser at the time of recombination, and the slightly cooler spots correspond to regions that were slightly less dense. The pattern of these anisotropies tells us profound things about the universe's geometry and composition, the size of the hot and cold spots, the way they're distributed across the sky, the correlation between spots of different sizes. All of these features encode information about cosmic parameters. From studying the CMB, scientists have determined the age of the universe to within 1%. The density of ordinary matter and dark matter, the amount of dark energy, and the geometry of space. They've confirmed that the universe is spatially flat and that inflation occurred. The CMB is a Rosetta Stone for cosmology, allowing us to decode the history and composition of the cosmos. These density variations are the seeds of all cosmic structure. The slightly denser regions would go on to collapse under gravity, pulling in more matter and eventually forming galaxies and galaxy clusters. The less dense regions would become the vast cosmic voids, the nearly empty spaces between galaxy clusters. By studying the pattern of these temperature variations in the CMB, cosmologists can learn about the initial conditions of the universe and test different theories of cosmic origin. Multiple space missions have mapped the cosmic microwave background in increasing detail. The Cosmic Background Explorer, or COBE, launched in 1989, was the first to detect the tiny temperature variations. The Wilkinson Microwave Anisotropy Probe, or WMAP, launched in 2001, provided much more detailed measurements. And the European Space Agency's Planck satellite, which operated from 2009 to 2013, created the most precise map of the CMB we have to date. These missions have allowed cosmologists to measure the age of the universe to within 1%, to determine the proportions of ordinary matter, dark matter, and dark energy, and to test theories of cosmic inflation. The patterns in the CMB match the predictions of inflation remarkably well, providing strong evidence that the universe did indeed undergo that period of rapid expansion in its first fraction of a second. The CMB also tells us something profound. We are looking back in time. Because the speed of light is finite, when we observe distant objects, we're seeing them as they were in the past. The light from the sun takes 8 minutes to reach us, so we see the sun as it was 8 minutes ago. Light from the nearest star, Proxima Centauri, takes 4 years to reach us, and the cosmic microwave background, that faint glow from all directions, shows us the universe as it was 380,000 years after the Big Bang, nearly 14 billion years ago. This is the surface of last scattering, the moment when photons last interacted with matter before streaming freely through space. We cannot see past this moment using electromagnetic radiation because before recombination, the universe was opaque. The CMB represents the oldest light we can detect, the edge of the observable universe in time, if not in space. It's a window onto an era when the universe was young, when there were no stars yet, no galaxies, just the faint glow of cooling plasma beginning to transition into the transparent cosmos we inhabit. Close your eyes and imagine it. Picture the entire sky glowing softly with this ancient light, stretched and cooled by billions of years of cosmic expansion, but still carrying information from that moment of transition. Every direction you look, you're seeing the universe at 380,000 years old, frozen in time like a photograph. The cosmic microwave background is a gift, a direct connection to the early universe, and it continues to reveal its secrets as our instruments grow more sensitive and our theories more sophisticated. The dark universe, what we cannot see. Here's a startling fact. Everything we can see, everything we've ever observed with telescopes or touched with our hands, all the stars and galaxies and planets, all the gas and dust and radiation, everything we think of as the universe, makes up less than 5% of the total mass and energy in the cosmos. The rest, the vast majority of what exists, is invisible to us. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can directly detect. This is the dark universe, dark matter and dark energy, two of the most profound mysteries in modern cosmology. Let's start with dark matter, because it's the simpler of the two, though still deeply mysterious. Dark matter is a form of matter that interacts with ordinary matter through gravity, but apparently through no other force. It doesn't emit photons, so we can't see it. It doesn't absorb photons passing through it, so we can't detect it by blocking light. It's completely transparent to electromagnetic radiation. And yet, we know it's there because we can see its gravitational effects. The first hints of dark matter came in the 1930s when astronomer Fritz Zwicky studied the Coma cluster, a large group of galaxies. By measuring how fast the galaxies were moving, he could calculate how much mass the cluster needed to have to hold itself together gravitationally. The answer shocked him. The visible matter, the stars and gas he could see, accounted for only about 1% of the mass required. There had to be vast amounts of unseen matter, which he called dark matter, providing the extra gravity. Most astronomers didn't take Zwicky's idea seriously at first. But in the 1970s, astronomer Vera Rubin made observations that couldn't be ignored. She measured the rotation speeds of stars and spiral galaxies, expecting to find that stars farther from the galactic center would move more slowly, just as outer planets in our solar system orbit more slowly than inner planets. But that's not what she found. Stars at the edges of galaxies were moving just as fast as stars closer to the center, sometimes even faster. This could only mean one thing. There was much more mass in these galaxies than could be accounted for by visible matter. Dark matter had to exist in a vast halo surrounding each galaxy, providing the gravity to keep those outer stars in their rapid orbits. Rubin's work was painstaking and meticulous. She spent decades observing galaxy after galaxy, and the pattern held consistently. Her colleague, Kent Ford, had developed a highly sensitive spectrograph that could measure the Doppler shifts of stars with unprecedented precision, allowing them to map rotation curves in detail. What they found violated expectations based on visible matter alone. The rotation curves stayed flat far beyond where the visible matter ended, indicating invisible mass extending well beyond the luminous disk of each galaxy. Rubin's discovery was particularly significant because it was independent of Zwicky's observations. Zwicky had looked at galaxy clusters, massive collections of hundreds or thousands of galaxies. Rubin looked at individual galaxies, systems millions of times less massive than clusters, yet both found the same conclusion. There was far more mass than could be seen. Dark matter wasn't just present in galaxy clusters, it was everywhere, an essential component of every galaxy in the universe. Since then, evidence for dark matter has accumulated from multiple independent sources. Gravitational lensing, the bending of light by gravity predicted by Einstein's general relativity, shows that galaxy clusters contain far more mass than we can see. The cosmic microwave background's temperature patterns encode information about the density of matter in the early universe, and that density is much higher than ordinary matter alone could provide. The large-scale structure of the universe, the way galaxies are distributed in vast filaments and sheets, matches what computer simulations predict when they include dark matter, but doesn't match simulations that only include ordinary matter. Dark matter appears to make up about 27% of the universe's total mass and energy. It's distributed in vast halos around galaxies and permeates galaxy clusters and the filaments that connect them. Current theories propose it's made of particles that have mass and feel gravity but don't interact with light or ordinary matter in any other measurable way. These hypothetical particles are sometimes called WIMPs, which stands for weakly interacting massive particles. Other candidate particles have been proposed, including axions and sterile neutrinos, but as of now, we haven't directly detected any dark matter particles in laboratory experiments, despite decades of searching. The evidence for dark matter's existence comes entirely from its gravitational effects on visible matter and light. The role of dark matter in cosmic history cannot be overstated. After recombination, when ordinary matter decoupled from radiation and the universe became transparent, ordinary matter was still relatively smooth and evenly distributed. But dark matter had been clumping for hundreds of thousands of years already. It doesn't interact with light, so it wasn't held back by radiation pressure the way ordinary matter was. Dark matter could collapse under its own gravity, while ordinary matter was still trapped in the photon bath. This gave dark matter a head start. By the time ordinary matter could move freely and start collapsing, dark matter had already formed structures. These dark matter halos acted as gravitational wells, drawing ordinary matter into them. Gas clouds of hydrogen and helium fell into these invisible scaffolds, and there they could cool, condense, and eventually form the first stars. Dark matter shaped the universe's structure, creating the framework upon which all visible structure would later hang. Then there's dark energy, which is even more mysterious and even more dominant. Dark energy makes up about 68% of the universe's total mass and energy, meaning it's more than twice as abundant as dark matter and more than 13 times as abundant as ordinary matter, and we have no idea what it is. What we do know is what dark energy does. It causes the expansion of the universe to accelerate. This discovery, made in 1998 by two independent teams studying distant supernovae, was completely unexpected and won the Nobel Prize in Physics in 1998-2011. Before this discovery, astronomers assumed that the expansion of the universe was slowing down, as it should if gravity were the dominant force on cosmic scales. But the observations showed the opposite. The universe's expansion is speeding up. This acceleration requires some form of energy that doesn't clump or dilute as space expands, and which has a repulsive gravitational effect. Einstein's equations of general relativity allow for such a thing, something he called the cosmological constant, a property of space itself that creates a kind of anti-gravity. Einstein originally introduced the cosmological constant to keep the universe static, which was the prevailing belief at the time, but he abandoned it after Edwin Hubble discovered that the universe was expanding. He reportedly called it his greatest blunder. But now it seems the cosmological constant, or something very much like it, might be real after all. Dark energy may be the energy inherent in empty space itself, what's called vacuum energy. Quantum mechanics tells us that even empty space isn't truly empty. It seethes with virtual particles, particle-antiparticle pairs that pop into existence and annihilate in tiny fractions of a second. This quantum activity has energy, and if that energy has the right properties, it could act as dark energy, driving cosmic acceleration. This represents one theoretical explanation. But there's a massive problem with this explanation when physicists try to calculate how much vacuum energy there should be based on quantum field theory. They get an answer that's about 10 to the 120th power times larger than what we observe. That's 1 followed by 120 zeros. It's arguably the worst prediction in the history of physics. Something is deeply wrong with our understanding, but we don't yet know what. Alternative theories propose that dark energy isn't a constant property of space, but a dynamic field that changes over time. sometimes called quintessence. Others suggest that our theory of gravity itself, general relativity, may need modification on cosmic scales. But as of now, we don't have a satisfactory explanation for dark energy's existence or nature. What we do know is that dark energy's influence grows over time. In the early universe, when everything was much closer together, gravity dominated. Matter, both dark and ordinary, was pulling things together, causing structure to form. But as the universe expanded and the density of matter dropped, dark energy's influence became more significant. About 5 billion years ago, dark energy became the dominant force, and the universe's expansion began to accelerate. This acceleration will continue indefinitely, barring some change in dark energy's properties that we haven't observed. The future of the universe depends on dark energy and remains uncertain. If it remains constant, the universe will expand forever, growing colder and more dilute, stars burning out, galaxies drifting apart beyond the reach of each other's light. This scenario is sometimes called the heat death of the universe, a quiet, cold ending. If dark energy grows stronger over time, a possibility some models allow, it could eventually tear apart not just galaxy clusters but galaxies themselves, then stars, then planets, and ultimately atoms in an event called the Big Rip. If dark energy weakens or reverses, which current observations don't support but can't completely rule out, the universe could stop expanding and begin to contract, eventually collapsing in a big crunch. We don't know which future awaits, and observations continue to refine our understanding. But we know that dark matter and dark energy, these invisible components that make up 95% of the universe, have profoundly shaped its history and will determine its fate. They remind us how much we still have to learn, how many mysteries remain at the heart of existence. The visible universe, for all its splendor, is just a small island in a dark cosmic ocean we're only beginning to map. The first light, when stars ignited the darkness. After recombination, after the cosmic microwave background was released and the universe became transparent, there followed a period that astronomers call the Dark Ages. This is something of a poetic name, but it's accurate. For hundreds of millions of years, the universe was dark. There were no stars yet, no galaxies, no sources of light except the fading glow of the cosmic microwave background itself, which was being redshifted into invisibility by the ongoing expansion. The universe at this time was filled with neutral hydrogen and helium gas, spread out in vast, thin clouds that followed the invisible scaffolding of dark matter. The temperature had dropped to just a few degrees above absolute zero. Everything was cold, dark, and quiet, but beneath this apparent calm, structure was forming. The seeds planted during inflation amplified into density variations visible in the cosmic microwave background were growing. Regions that were slightly denser were pulling in more gas. Dark matter clumps were becoming more concentrated. Slowly, over tens of millions of years, the first gravitationally bound structures began to take shape. These first structures were small by galactic standards, perhaps a few million times the mass of our sun, contained in regions a few hundred light years across. We call them mini-halos. They were dominated by dark matter, but they also contained significant amounts of ordinary gas, and as this gas fell into the dark matter's gravitational wells, it began to heat up from the compression. Given enough time and mass, the centers of these gas clouds would reach temperatures of millions of degrees, hot enough for nuclear fusion to begin, hot enough for stars to ignite. The first stars are called population 3 stars by astronomers, though they've never been directly observed. These stars would have been unlike any we see today. According to theoretical models, they formed from pristine gas, hydrogen and helium created in the Big Bang with no heavier elements, no metals as astronomers call them. This composition would have had profound implications for how they formed and how they behaved. Modern stars form from gas clouds that contain small amounts of heavier elements like carbon, oxygen, and iron. These elements are incredibly important for star formation because they're efficient at radiating away heat. When a gas cloud collapses, it heats up due to compression. That heat creates pressure that resists further collapse. If the cloud can radiate away this heat, it can continue collapsing and fragmenting into smaller clumps, eventually forming many stars. But primordial gas, with no heavy elements, couldn't radiate heat efficiently. It stayed hot, which meant high pressure, which meant the gas clouds couldn't fragment into small pieces. The cooling mechanisms available to primordial gas were limited to hydrogen molecule formation and very inefficient processes. Without carbon, oxygen, or metals to create spectral lines that could carry away thermal energy as radiation, the collapsing gas remained hot and resisted further fragmentation. This fundamental difference in cooling efficiency determined the entire character of first-generation star formation. As a result, theoretical models predict the first stars were massive. Where a typical star-forming region today might produce dozens or hundreds of sun-like stars and many more smaller stars, the first star-forming regions likely produce just one or a few extremely massive stars, perhaps 100 to 300 times the mass of our Sun based on computer simulations. These giants would have been hot and luminous, radiating intensely in ultraviolet light. Their surface temperatures may have exceeded 100,000 degrees Kelvin compared to our Sun's 5,800 degrees. They would have appeared in intense blue-white, though of course there were no eyes to see them and no atmosphere through which to view their light. When these first stars ignited, current models suggest perhaps 100 to 200 million years after the Big Bang, they ended the Dark Ages. Their light flooded out into the surrounding space, ionizing the hydrogen gas around them, creating bubbles of ionized gas in the neutral hydrogen ocean. As more stars formed, these bubbles grew and merged. Within a few 100 million years, based on observations and simulations, the entire universe had been reionized. The neutral hydrogen fog became transparent to visible light once again, and the universe took on a form more similar to what we see today. But the first stars didn't last long. The most massive stars burn through their nuclear fuel at prodigious rates, where our Sun will shine for 10 billion years. These massive population 3 stars might have lasted only a few million years, and when they died spectacularly in supernova explosions that were among the brightest events in cosmic history. These supernovae did something critical. They created and dispersed heavy elements. Inside these massive stars, nuclear fusion had proceeded beyond hydrogen and helium. Carbon, oxygen, silicon, iron, and dozens of other elements were forged in their cores and in the final explosive moments of their deaths. When the stars exploded, they scattered these elements into the surrounding space, enriching the gas clouds from which future generations of stars would form. This process, called stellar nucleosynthesis, is how all the heavy elements in the universe came to be. Every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood was created in the core of a star billions of years ago and scattered into space by a supernova. We are, quite literally, made of stardust. The story of how stars formed from the dark is also the story of how the elements that make life possible came into existence. Some of the most massive first stars may have collapsed directly into black holes without exploding, according to current models. These black holes, potentially ranging from dozens to hundreds of times the mass of the Sun, could have become seeds for the supermassive black holes that sit at the centers of most galaxies today. Over billions of years, they would have accreted gas and merged with other black holes, growing to millions or even billions of solar masses. While this remains an active area of research, it offers one plausible explanation for how supermassive black holes formed so early in cosmic history. As the first stars formed and died, they changed their environment. The radiation from stars heated the gas around them. The supernovae shock waves compressed nearby gas clouds, triggering new rounds of star formation. The heavy elements allowed more efficient cooling, which meant future star-forming clouds could fragment into smaller pieces, forming smaller stars that would live longer. The universe was transitioning from a first generation of massive, short-lived stars to a more diverse stellar population. By about 400 to 500 million years after the Big Bang, observations suggest the first galaxies had assembled. These early galaxies were small and irregular, nothing like the grand spiral galaxies we see today, but they were recognizable as gravitationally bound collections of millions or billions of stars. They clustered along the filaments of dark matter, forming a cosmic web that stretched across the universe. Gravity continued its patient work, pulling galaxies toward each other, causing mergers and interactions that would gradually build larger and larger structures. The James Webb Space Telescope, launched in 2021, is now peering back to these earliest epochs, observing galaxies as they appeared just a few 100 million years after the Big Bang. These observations are revealing a universe that's more complex and active than many astronomers expected, with surprisingly bright and structured galaxies forming earlier than previous models predicted. We're still learning the details of this era, still refining our understanding of how the first stars and galaxies came to be. But the basic story is clear. The universe went from darkness to light, from smooth and featureless to richly structured, from a state dominated by quantum fluctuations and dark matter to one filled with stars, galaxies, and the building blocks of life. The transformation took hundreds of millions of years, but in the grand sweep of cosmic history, it happened remarkably quickly. The universe was ready to light up, and when it did, it became the star-filled cosmos we recognize today. The cosmic web, architecture on the grandest scale. If you could step back and view the universe on its largest scales, billions of light years across, you would see something astonishing. Galaxies are not scattered randomly through space. Instead, they're organized into an intricate structure that looks like a vast spider web. Long filaments stretch across hundreds of millions of light years, dotted with galaxies like beads on strings. Where filaments intersect, enormous clusters of thousands of galaxies congregate. Between the filaments lie vast voids, regions containing very few galaxies at all. This is the cosmic web, the largest scale structure in the universe, and its existence was encoded in the universe's initial conditions, in those quantum fluctuations during inflation that we discussed earlier. After the first stars and galaxies formed, gravity continued to shape the universe. Dark matter, which had been clumping since shortly after the Big Bang, provided the framework. Ordinary matter, the gas and stars we can see, followed dark matter's lead, falling into the gravitational wells that dark matter created. Over billions of years, this process built ever larger structures. Imagine watching this happen in time-lapse. In the earliest epochs, you see small clumps of dark matter forming, drawing in gas, which condenses into the first stars and small galaxies. These early structures are like seeds. As time progresses, gravity pulls nearby clumps together. Small galaxies merge into larger ones. Streams of gas flow along the filaments, feeding the growing galaxies. The cosmic web becomes more pronounced. The filaments more defined, the voids more empty as matter concentrates along these preferred paths. This hierarchical growth from small structures to large ones is a natural consequence of how gravity works and how the initial density fluctuations were distributed. The pattern we see today, with its filaments and voids and clusters, emerged naturally from the initial conditions set during inflation. Computer simulations that start with these initial conditions and apply the laws of gravity produce cosmic webs that look remarkably like what we observe in the actual universe. The largest structures in the universe are galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. A typical cluster might span several million light-years and contain the mass of quadrillions of suns. The space between the galaxies in a cluster isn't empty. It's filled with hot gas at temperatures of tens of millions of degrees, heated by the gravitational energy of the cluster's formation and by supernova explosions from the member galaxies. This gas emits X-rays, which we can detect with space telescopes, revealing the extent and structure of the cluster. Clusters themselves aren't the largest structures. They're found at the nodes and along the filaments of the cosmic web, concentrated at intersections where multiple filaments meet. The filaments themselves stretch for hundreds of millions of light years, containing galaxies and dark matter in long strands, and between them lie the cosmic voids, vast bubble-like regions that can be over 100 million light years across and contain very few galaxies. Our own Milky Way galaxy is part of a small cluster called the Local Group, which includes the Andromeda Galaxy and about 80 smaller galaxies. The Local Group is itself part of a larger structure called the Laniakea supercluster, which spans 500 million light-years and contains about 100,000 large galaxies. We're moving through space along with the rest of the Local Group, drawn by the gravity of the denser parts of Laniakea, particularly a region called the Great Attractor. The cosmic web is not static. It's still evolving, still growing under the influence of gravity and dark energy. Galaxies continue to merge and interact. Filaments become more defined. Voids grow emptier. But the overall structure, the pattern of filaments and voids, was set in the early universe. The seeds planted during inflation, nurtured by dark matter through the dark ages, blossomed into the cosmic architecture we see today. One fascinating aspect of this structure is that it's similar at many scales. Galaxy clusters contain galaxies, but the galaxies themselves contain star clusters, and the way these star clusters are distributed within a galaxy sometimes echoes the way galaxies are distributed in a cluster. This property, called self-similarity or scale invariance, is a natural outcome of the hierarchical growth process. It hints at the underlying unity of the forces shaping the universe, from the quantum scale, where it all began, to the largest scales we can observe. The cosmic web also tells us about the future. As dark energy drives the acceleration of cosmic expansion, the filaments will gradually thin out. Galaxies within a given cluster will remain bound together, but clusters themselves will drift apart. Billions of years from now, the cosmic web will be less prominent, the voids larger, the universe more isolated and lonely on its largest scales. But for now, we live in an era when the universe is richly structured and beautiful to observe. From our vantage point on a planet orbiting a star in a galaxy, within a cluster, within a supercluster, within the cosmic web, we can look out and see the architecture of creation itself, the fingerprints of quantum fluctuations amplified to cosmic scales, the ongoing story of matter shaping itself under the patient pull of gravity. Our place in the story. Reflections on cosmic origins. Let's pause here at the end of our journey through cosmic history and reflect on what we've traced. We began at the singularity, a point of infinite density and temperature where our physics breaks down and our imaginations strain. We traveled through the Planck epoch where space and time themselves were quantum and uncertain. We witnessed cosmic inflation, that incredible instant of exponential expansion that set the stage for everything to come. We watched the universe cool in its first second as the fundamental forces separated and the first particles formed. We saw matter gain a slight edge over antimatter, ensuring that something would remain when annihilation was done. We observed the first atomic nuclei form in those crucial 15 minutes of Big Bang nucleosynthesis. We waited through hundreds of thousands of years until the universe cooled enough for atoms to form and light to stream freely, creating the cosmic microwave background that we can still detect today. We learned about dark matter and dark energy, those invisible components that dominate the universe's composition and evolution. we witnessed the Dark Ages end as the first stars ignited, massive and luminous, forging heavy elements in their cores and dispersing them through supernovae. We saw small galaxies merge into larger ones, structure forming along the scaffolding of dark matter, the cosmic web taking shape over billions of years. And here we are, nearly 14 billion years later, on a small planet orbiting an ordinary star in an unexceptional region of a typical spiral galaxy. Yet from this vantage point, through careful observation and brilliant reasoning, human beings have managed to reconstruct this entire story. We've looked back to the beginning using telescopes and particle accelerators and mathematical models. We've detected the cosmic microwave background, measured the abundances of elements, observed the large-scale structure of the universe, and found that it all fits together, that it all tells the same story. This story is extraordinary in many ways. Consider the precision required. If the density of the universe at 1 second after the Big Bang had been different by 1 part in a quadrillion, either the universe would have collapsed back on itself within moments or expanded so rapidly that no structures could ever form. If the strength of the strong nuclear force were slightly different, atomic nuclei couldn't exist. If electromagnetism were slightly stronger or weaker relative to other forces, chemistry as we know it would be impossible. The universe appears to be finely tuned for the existence of complexity, for the formation of stars and galaxies and planets, and ultimately life. This observation has sparked much debate. Some see it as evidence of design, suggesting that the universe was deliberately crafted to allow for our existence. Others point to theories like eternal inflation and the multiverse, which propose that our universe is just one of countless universes, each with different properties, and we naturally find ourselves in one where life is possible because those are the only universes where observers can exist to ask the question. Physicists have cataloged dozens of these apparent fine-tuning coincidences. The cosmological constant, for instance, has a value that allows the universe to expand at just the right rate. If it were much larger, space would expand so rapidly that galaxies couldn't form. If it were much smaller or negative, the universe might have collapsed long ago. The mass of the electron, the charge of the proton, the ratio between the strengths of different forces, all of these seem to fall within narrow ranges that permit complex chemistry and stable stars. Change any of them by more than a small percentage, and the universe becomes inhospitable to life as we know it. The anthropic principle addresses this puzzle by noting that we shouldn't be surprised to find ourselves in a universe capable of producing observers because we couldn't exist in any other type of universe. It's a selection effect. If countless universes exist with different properties, we naturally find ourselves in one of the rare ones that permits our existence. But this explanation, while logically sound, doesn't satisfy everyone. It seems to push the mystery back rather than solving it. Why should there be any universes at all? Why should the multiverse, if it exists, have the properties it does? We don't know the answer. We may never know. But the question itself is profound. Why does the universe exist at all? Why does it have the laws and properties it does? Why is there something rather than nothing? These questions touch on philosophy and theology as much as physics. They remind us that science, for all its power and success, operates within certain boundaries. It can tell us how the universe behaves, how it evolved, what it's made of. But the deepest questions of why, of meaning and purpose, remain open. What we can say is this: you are part of this story. The atoms in your body were forged in stars that died billions of years ago. The water you drink contains hydrogen that formed in the first 3 minutes after the Big Bang. The calcium in your bones, the iron in your blood, the carbon in your cells, all of it was created in stellar furnaces and supernova explosions. You are made of the universe, and the universe is made of you. More than that, you are the universe becoming conscious of itself. Through your eyes, the cosmos observes its own structure. Through your mind, it contemplates its own origins. The fact that matter and energy, following the laws of physics over 14 billion years, can organize itself into thinking, feeling beings capable of understanding where they came from. This is perhaps the most astonishing part of the entire story. We don't know if life exists elsewhere in the universe. The cosmos is vast, with billions of galaxies and trillions of planets, so it seems likely that we're not alone. But we don't know. Perhaps intelligence and consciousness are rare, unlikely outcomes that required countless improbable steps. Or perhaps they're common, inevitable consequences of chemistry and time. Either way, the fact that you exist, that you can lie here and listen to this story and comprehend it, is a kind of miracle. The universe is still young, still evolving. Stars continue to form and die. Galaxies merge and interact. Dark energy drives the accelerating expansion. Current models predict that in a few billion years, our Milky Way will collide and merge with the Andromeda Galaxy, creating a larger elliptical galaxy. In tens or hundreds of billions of years, star formation will slow and eventually cease as gas is used up. In trillions of years, even the longest-lived stars will burn out, and the universe will grow dark and cold. But that ending is unimaginably far in the future. For now, we live in the stelliferous era, the age of stars, when the universe is vibrant and luminous. We live in a time when beings like us can exist, can look up at the night sky, can build telescopes and particle accelerators, can ask questions about where we came from and where we're going. This is our moment in cosmic history, a brief flicker in the vast expanse of time, but a remarkable moment nonetheless. So as you lie here feeling the weight of your body, the rhythm of your breath, remember that you are ancient. The particles that make you up have existed since the beginning. They've been in stars and in the space between stars. They've traveled billions of light years, and they've come together in this precise arrangement to create you. You are a way for the universe to experience itself, to know itself, to tell its own story. The birth of the universe was the birth of everything, including the potential for this moment, for your existence, for this experience of wonder and understanding. From nothing, or from quantum foam, or from a multiverse of possibilities, came everything. Came space and time, matter and energy, stars and galaxies, planets and life, and eventually consciousness capable of looking back and marveling at the journey. This is the story of the universe. It's also your story. And as you drift towards sleep now, carry it with you. Let it fill you with wonder. Let it remind you that you're part of something vast and ancient and beautiful. Let it give you perspective on your place in the cosmos. You are small, yes, compared to galaxies and superclusters, but you are also essential, a unique expression of the universe's infinite creativity. If you enjoyed this journey through cosmic history, I invite you to like, subscribe, or share your thoughts below. It helps others find their way here too, one sleepy soul at a time. For now, let your breathing deepen. Let your thoughts slow and drift. Feel your body sinking into rest, held by the earth, which is held by the sun, which orbits within the galaxy, which moves through the cosmic web, all of it dancing to the rhythm of gravity and expansion that began 13.8 billion years ago. Close your eyes, release the waking world, and sleep well, knowing that you are stardust contemplating stars, the universe dreaming of itself. A brief and precious moment of consciousness in the long, slow unfolding of cosmic time. Good night.